It's the 2nd of March 2026, and welcome to this British Astronomical Association Hydrogen Line Radio Astronomy Group meeting. It's a real pleasure to see you all again today, especially given the world events, which are probably frightening everybody. But we've got some exciting stuff, hopefully to take your mind off that tonight. And particularly, we're going to start tonight with Wolfgang Herrmann, who has very kindly offered to speak to us about his experience of Hydrogen Line over many years and the lessons that he's learned from that, and things for us to better help to learn towards our own kit and the way that we're doing it, hopefully. Then after that, we've got 2 or 3 other people who have volunteered to speak on issues of interest to themselves, who I'll introduce nearer the time. And then, as usual, there'll be a chance for everybody to talk on things that are of interest related to Hydrogen Line radio astronomy, one at a time. So, as we're quite a bit on the agenda, I'm going to get started and say thank you very much, Wolfgang, for joining us tonight, and may I pass the floor over to yourself.
Yeah, thank you very much. It's my pleasure to be with you tonight, and as you can imagine, I have a very simple title for my talk tonight. It's hydrogen.
So sorry, Wolfgang, a second. My apologies. I'm just going to mute everybody, so you might need to just unmute yourself again.
And we see the smaller picture with the little pictures down the left.
Wait a minute. Yeah, you'll need to unmute yourself again, Wolfgang, sorry.
Okay, so let me start over again. Okay, so now you should be hearing me, hopefully.
Indeed, yes, and we can see your presentation as well.
Okay, very good. Okay, once again, simple title of my talk, it will be hydrogen. And the outline of the talk, I would first like to talk a bit about the history of things. Then cover a bit of the equipment and tools for observations. I understand quite something of that has already been discussed in this group, so I'll probably skip over a couple of things. I want to address the question, bigger antennas versus smaller antennas, and some of the surprises that you can get there. We need to talk about velocities, the classical experimental rotation curve, and then I want to talk a bit about extragalactic hydrogen and another subject which I call exotic hydrogen. So that's sort of the outline for today. And I really would like to start with something which I call having fun with history.
No, Wolfgang, we see the preview with the little slides down the left-hand side. You are not advancing slides for us.
Okay, so that's different.
Perhaps sharing the wrong window.
Yeah.
Thank you.
So, no, we're not getting there where I want to be.
I tend to find the best way to do it is to just share the whole screen rather than an individual window.
Yeah, I think that's what I'm going to do. So share this. Does that work now?
I think so. Yeah, we seem to have 2 different slides pop around there. Just try advancing a slide a second. Yep, it's working fine.
Okay. So this was the outline. I'm not going to repeat that and really go on and discuss what I call having fun with history. This is a part of a publication, and I've deliberately redacted the author for the time being so that you can have a guess later on who that was. Now, this is in the Dutch language, and I will read the English translation to you. Although the existence of radio waves of an extraterrestrial origin has been known for a decade, astronomers have paid little attention to them. This is partly due to the limited data that observations have yielded thus far. Much more than an order of magnitude of intensity and the rough directional dependence of the radiation has not been established. Therefore, little can be expected from a precise discussion of the observational data. On the other hand, from a purely theoretical standpoint, the existence of these waves is not particularly interesting. In the physical state of interstellar gas, the production of radio waves is not at all a significant feature. The amounts of kinetic energy converted into radiant energy by this process are so small that as small leaks, they are completely negligible in the large energy budget. So obviously, this is the introduction of somebody who doesn't believe in radio astronomy. So you can't see anything, and it's theoretically completely uninteresting. So this publication goes on and very thoroughly goes through the different processes that one could imagine at this time that could produce radio energy from outer space. So I'm not going to go through all of that and just skip over to a later section of this publication, and where he addresses another possibility. And again, I put the English translation on that. As all these lines, like the free continuum, would only be formed in H2 regions. But there is still a completely different possibility. The ground level of hydrogen is split into two levels with a distance of 0.04 inverse centimeter. That's an energy way of describing energy, due to hyperfine structure. In one state, the spins of the electron and proton are aligned, while in the other state, they are opposite. A spontaneous flip of the spin would emit a quantum of 21.2 centimeter wavelengths. Of course, such a transition is forbidden. And then he continues doing all sorts of calculation about the possible intensities and so on. And just he finishes off with, since Sm is usually of the order 1, the situation does not look hopeless, even if we consider that the sensitivity of current receiving systems require a factor of 100 higher sensitivity. However, there are reasons to assume that the actual Sm will be considerably smaller. Until a rigorous calculation has been made, the existence of this line remains speculative. So my question to the audience is, does anybody have an idea who wrote this? Anyone?
I hope it wasn't Vanderholst.
No? Somebody
I
else?
will guess Oort.
No, not Oort. Earlier than Oort. Okay, I'll tell you. Henk van der Hulst. That was the one who predicted the existence of the 21 centimeter line. So this is the original publication that predicted that, or he said it remains speculative. And the interesting thing, that's why I like this so much, is because he was the poor guy who was instructed by his PhD supervisors to sit down and do all the calculations what might be possible in radio astronomy. And he didn't like it. He just wrote down, this isn't interesting, cannot be seen, this doesn't work, and so on. And he continues. And at the very end, he says, well, that there's something where it's not hopeless, but it remains speculative. So I find this interesting that this person who predicted that was quite skeptical when he started things. And he became a famous radio astronomer later on, so he changed his mind about radio astronomy. I find this funny, and of course, if a theoretical person like him says, well, it remains speculative, and we'll see what happens, then the observers come up, and in fact, a couple of years later, it was published in 1951, the first observation of this line was reported. It was almost simultaneously observed by two groups in the US and in the Netherlands. On the picture on the right-hand side, you see a UN and the horn antenna that was used at the time, and the graph there is showing the line. It is both in a positive and negative, which has something to do with the way they, the technique that they use, which is called frequency switching, which means that the line will show up both positive and negative. That's a way of getting rid of the baseline. So this is where it all started. The prediction in 1945 and the first observation in 51. And we've come a very, very long way since then. So if we look at the hydrogen line today, particularly from an aspect of an amateur astronomer, it's really excellent for beginners. The equipment is easy to build. There are so many options for antennas. It's a good starting point to learn things and to go later on into more advanced stuff. And there's some interesting physics that you can actually see. And the picture on the right-hand side shows the principle again. You have the hydrogen atom. When it's in excited state, proton and electron are aligned. And when they flip, they release a difference in energy as a photon or a radio wave at 21 centimeter wavelengths. So this is what it is all about, and we'll see how we can observe that. So that's the starting point. How can we observe that? What are the ingredients that you need? First of all, obviously you need an antenna, and I had a look at the recordings of your previous session, so there's been some discussion about that already, so I don't go in too much detail, but just want to highlight a few things. Then obviously you need a low noise amplifier. In many cases you will need a filter in order to get rid of other strong signals. It will depend on your particular location. And the third, by the way, typically you would call the low noise amplifier filtering, so all the analog part, the front end in radio astronomy speak, and the other part for the analysis is the back end. So these days you do typically use software-defined radios. There are other options as well, but really software-defined radios are the way to go. And if it's a software-defined radio, you need a PC and the software to go with it. So these are the elements that are needed in various kinds. So let's first have a quick look at the antenna, which obviously has been discussed in this group. So there are really, really many options that you can use. On the, let's call it high end, just a quick question, can you see me when I move my cursor around?
We see your cursor.
Oh, very good. So this is the 3.3 meter dish by the late Jean-Jacques Mantoux, a very excellent instrument. He's done a lot of things, and I'll show some of that. Many of you know the scope in the box, a small semi-parabolic antenna which can be used. Another example is a horn antenna. This is a design by the West Virginia University. Then something that has been discussed also here, I think Heather did some discussion of that, which is frequently called a coffee can, which is essentially a circular waveguide. We tend to make these from stovepipes, but yeah, anything that is about 15 centimeter in diameter will work. And it can even use a simple dipole. This is a dipole with a balloon, so that the symmetrical is converted to a coaxial. The basic message here is anything goes. Whether it's a bigger antenna or a very small antenna, they are all suited to see the hydrogen line emission. And there's a favorite saying that I always use in this context. I say anything short of a wet shoestring will work as an antenna for hydrogen. I haven't tried the wet shoestring, so this is a fairly straightforward path that one can go. The next thing that you will need is a low noise amplifier. And these days a very popular approach is to use the Sawbird from, Nolek. That's a amplifier, which has a noise figure, a very decent noise figure of 0.55 dB. And the advantage is it has an integrated filter, so that's really all you need. A very low-cost solution is a device which is sold on eBay, which is an amplifier based on a specific amplifier module. They used to be quite good, so we measured them at 0.6 dB noise figure. However, recently it seems that the quality varies. We have received some that were only 2 dB in noise figure. And the reason may be that the device that's inside has been discontinued by the manufacturer. And so maybe they're just selling off some of the devices that were simply out of spec. So they are still quite usable as a second stage amplifier, just in case that you need to have a little bit more gain. On the high-end side, there's something sold by the company Kuhne, which is a what they call a super low noise amplifier. They specify it at 0.4 dB. We have actually measured it at 0.3 dB, so they're conservative with their specification. So if you want to spend some money, by the way, I don't have a price for that, but that's an excellent amplifier as far as we can tell. One remark on the filter, if you want to use a separate filter because you're using something like the Kuhne amplifier, there's an excellent design by Matthias Wittmar, and that's a cavity filter that can be very easily made because it doesn't require any milling. It's just taking standard size components, and they're fairly easy to make, and they're excellent. Once they're aligned, then they're really excellent. We have built some of these, and we have insertion losses like 0.2 dB from that, so very excellent, very flat response, so very nice things. So these are things that are also reasonably easy to do and to get. So what is next? The next thing is the software-defined radio. By the way, just one remark, if somebody has a question in between, I'm happy to answer questions also in between. So just interrupt me and I'll be happy to respond. Okay, software-defined radios. This is a list of software-defined radios that I'm aware of. There may be one or two others. There is a very low-cost solution which many people use, the RTL SDR. They come in very many variants these days, but they're fairly cheap, and they have their drawbacks, like all of these that are listed here. There are pros and cons. This is a fairly wavy background and also a limited bandwidth. Then there's a long time around already, the HEC RF1. Then there's a Lime from Lime Microsystems, I think they're called, Lime SDR. That's a more capable device that has been discontinued originally, but now is back and is again produced because obviously the demand has been big enough, so it's quite a good device. Then there is the analog devices ADA and Pluto, shown here below. Many people use the AirSpy. Then another option is the SDR Play. And then there's a product line from Ethos Research, which are more pricey. In particular, the B210 and the B205 Mini are used in the amateur arena. So these are good instruments. And then there's the Blade RF. We have actually tested almost all of them, with the exception of the Blade RF. We don't have a Blade RF, but all the others are, I would say all of them have some disadvantages as well. So there's no ideal one, but of course they are more different in capability and so on. But as far as the reception of the hydrogen line, essentially you can use all of them with more or less difficulties as far as the baseline is concerned. I should also mention that there are very clones of these made by Chinese manufacturers. I don't have much experience with that. I do have a clone of the HEC RF1, and that works not quite as good as the original one. It has some spurious lines and so on, but once I upgraded the firmware, it actually worked and can be used as well. But having said that, I don't have any experience with the other clones. There are clones from the Pluto, there are clones from the Atlas Research products. I don't know how they work. Listening to the previous talks, the FunCube dongle has been mentioned, and I would say that's not very useful for hydrogen. The reason is that it has a limited bandwidth. It's about 190 kilohertz, if I remember, and that's smaller than the bandwidth of the hydrogen line, so you would have to scan. That's not really what you want to do. But as a summary, there are many variants of SDRs that can be used for the purpose. So that's a big choice there. Now, when you have a software-defined radio, the next step is the software. And I've made a list here of the software that can be used for hydrogen line observations. The list is in no particular order. It's just I came across them, or when I put the slides up, the sequence that I did, but the sequence doesn't give any preference or whatsoever. So the first one on the list is called GR Radio Astro, which was done by the West Virginia University. Had a previous version of that, but I think that's the latest version. It does support all SDRs. I put a question mark behind that because I think it does support all SDRs that are supported by GNU Radio. And but they have only tested it, I think, with the SPI. And but I'm fairly confident that that would work with all different SDRs that are supported by GNU Radio, and it's has been tested on Linux. Then there's Ezra by Ted Klein, which has been discussed quite a bit here, and also discussed in all forums and so on, which is under very active development. And Ted, you need to correct me. As far as I recall, at the moment, it's only supporting the RTL SDR. I know, if I recall correctly, you're working on others as well, but that's not finished yet. Is that correct?
Not quite finished, at least not posted. That's correct. But
Okay,
great success with the new radio and SOAPy drivers as well. So that makes the list much larger.
Yeah, definitely. Once you have SOAPy as the underlying driver or GNU Radio, that will work. So we're looking forward to see that list completed and the updated version released. So also my understanding that people have been using it both under Linux and Windows. So that's in that way fairly flexible. Then there is again a GNU Radio based program, Spectral Radiometer by Marcus Leach. It supports all SDRs because it's GNU Radio based, and Marcus is a very big believer in Linux and Linux only, so he has only tested it on Linux. What else is available? There's Virgo. That's developed by Apostolos Banakis Misilis. I hope I spelled that correctly. That's also in a way based on GNU Radio. It's not so obvious, but under the hood he's using GNU Radio elements, and that also allows that all different SDRs are supported. And that's certainly worthwhile looking at. For those who are, let's say, limited or inclined to use Windows, there's one solution already a couple of years around, I think, which is I would call it a wrapper on top of SDR Sharp, made by Michiel Klaassen from the Netherlands. He's using that. I don't know how much it is used in the community, but that is certainly an option for people who are not too much inclined to go onto Linux. And along the same lines, we have SDR sharp with the IF average. I think that's used reasonably frequently. Again, can be used on Windows. And then this originally was developed for the AirSpy. My understanding, it can be used with other SDRs as well via plugins. Okay, that's not the full list yet. We have two more, both made by Victor Bersen from Denmark. His first development is called H-Line. It's RT-LSDR only, both for Linux and Windows. And a more recent development is called Radio Pi, which actually will support, I understand, all SDRs. He makes, on his website or on the GitHub, he makes a remark that he hasn't tested it yet all, but it should be quite capable of using all the SDRs, because also this has, as far as I know, a background on GNU Radio. Okay, so as you can see, there are many options. Certainly worthwhile looking into some of these. All, again, have pros and cons, and I don't have a specific recommendation in particular, because we don't use any of these. I'm afraid I have to say that. We are using two programs developed by us. One is called Spectrometer 2, because it's the second version of something that we did earlier. Another one is called USRP Spectrometer, because it's directly or specifically for the Ethos products. Now, why are we not using any of the nice things that are around? Partially it has historical backgrounds, but there's some key reasons why we do that. Number one reason is data formats. We simply have to use data formats that are used in the professional community, because we do a lot of data exchange with universities and other research institutions. And we just have to sort of go with them. Another aspect is that we have these programs integrated with our control system. So the programs talk to our telescope control systems, so they can get all the information about pointing and what target we are looking at and so on. And of course, this is not, because it's specific for our telescopes, that is not supported by the other programs. Another aspect is that we need higher bandwidth, we need dual polarization. None of these, as far as I know, none of these programs, the other ones, support dual polarization at the moment. Then another thing I will come back later is support of LSR correction. And also we need the support of various spectral lines like water masers, OH masers, and so on. So there are certain specific requirements that we have. Now, the question that will come up, why do we offer that on GitHub? The reason for that is the concern that we will not be able to support it. Ted Klein will know that best, that if you open that to the general public, you will inevitably get questions back, and that has to be respected. And we simply don't have the resources, so we don't want to disappoint people. And of course, the integration with our control system is something that would have to be taken out, because it's would not work with other telescopes. So we have, in some cases, upon request, gave that program to others. With the explicit notice, please, if you have run into problems, we will not be able to support it. And I also offer this here. We can certainly, upon request, provide these programs, maybe for their own modification and so on. But if questions come up, there will be extremely limited resources to support that. So please accept my apologies for that. Okay, so we do have now all the ingredients together that we need. We have an antenna, we have low noise amplifiers with filters or without filters. we have an SDR, one sort or another, and we have the software to go with it. So we are ready to do observations. Now, let me give you a first example. This is a spectrum taken with our 3-meter dish. So on the left-hand side, you have a single spectrum at some place in the galactic plane, essentially. And on the right-hand side, you see a transit scan. This is at our location looking straight up. So the telescope is looking straight up. And what you see here in this graph is it's a full day, so full circulation of the Earth, 24 hours in right ascension, looking straight up, so constant declination. And the vertical scale is the velocity of the hydrogen line that we observe, and the color denotes the intensity. So it's showing that the galactic plane with a high intensity passes through the beam twice, as you would expect. Now, if we take the same scenario and instead of taking a 3-meter dish, take a simple dipole, it looks like that. So, again, of course, if a dipole is looking straight up, it's not only just looking straight up, it's looking over a wide range because of the high opening angle of a dipole. But you can get a fairly decent spectrum here, and also a fairly decent, of course, much noisier, but a very distinct dual transit of the galactic plane. And that shows something that the difference, yes, it is there. You have a completely different resolution, and of course also a different intensity, but not the difference that you would expect between a 3-meter dish and a simple dipole. I mean, it's not that extreme. And that's something that's actually worthwhile looking into. And I call it the miracle of small antennas, which I'll explain right here. So what is happening? Let's see. Here's our telescope. And we assume we have two different telescopes. One with a smaller diameter, which has a wide opening angle, like this. And then we have a bigger antenna with a smaller opening angle. Now, let's make a rough calculation of how much power do we receive from this hydrogen cloud. Obviously, it will depend on the collecting area. So it goes with a square of the radius of the dish, if it's a dish. So this is the collecting area. But then we also have to consider how much hydrogen do we actually observe? How big is the area, the surface area that we are looking at? And this is the opening angle of our telescope. The opening angle is roughly 1.22 times the wavelengths divided by the diameter of the telescope. And so this is the angle, and the sine, the area that we see is the sine of, is the sine of that squared, because we are looking at an area. So this is roughly so this is proportionally to what the power that we have. Now, if we have fairly small angles, so not extremely wide opening angles, x, the equation holds that x is equal to the sine of x, or at least roughly. So the sine disappears, and we look at this formula to that, and then we can see one thing. R cancels. We have r squared here, and there's r squared in the denominator here. So the received power is independent of the diameter of our telescope, which is surprising. And that holds as long as the opening angles, or the hydrogen cloud, really fills the complete beam. So if it's a large cloud, a wide cloud, which hydrogen is, it is really that a small antenna can see quite some intensity just because it's looking at a large area. So in other words, the beam filling factor is constant. If you think that to the extreme, if the hydrogen would be completely uniform distributed over the sky, the size of the antenna wouldn't matter at all. It does matter when it comes to resolution. So if you want to see certain structures like if it's structured, things look different here than here. But in general, the principle is that small antennas, because they are looking at a large part of the sky, which is all filled with hydrogen, can get a very decent signal. And that's why hydrogen observation is so easy for amateurs with a small instrument. And I call this the miracle of small antennas. That helps a lot. Okay, another thing that we need to talk about is velocities. There's one thing, when velocities are measured, we are measuring the velocity between ourselves and the hydrogen cloud. So we are looking from our observatory towards a hydrogen cloud. And as the Earth moves around the sun, and also we are turning, the Earth moves around itself, the measured velocity is dependent on the time and the location of the observation. Just think about it. If we're sitting on Earth, we are moving one direction, and let's say at some point we're moving towards the hydrogen cloud. Half a year later, we're on the other side of the sun, we're moving away from it. So it really depends on the location of our measurement and the time, what velocity we measure. And obviously this is messy. I mean, this is not something that you want to have. So how do you take care of that? What you do is you define a reference frame, and always relate the velocities to this frame. And there's this convention that's called the Kinematics Local Standard of Rest. That's basically, you take as a reference frame the solar system barycenter, and also you add a certain peculiar motion of the solar system within the local group. That's something to do with the fact that we are interested in the velocity of within our galaxy, and our sun does something specific. It moves in a certain direction, so we take that out. That is a pure convention. So what I would recommend to everybody, if you want to do what I call serious stuff, that is, you want to evaluate your data, I would recommend always use the LSR corrected velocities. And I don't go into the details of how to do that, but I have some links that give you background information and all the details and how to calculate that. So that's something that should not be neglected. And in order to demonstrate that, I will switch back to a previous slide. I hope you can all see that there is a curved line here. That is actually a fixed frequency RFI. So it's one fixed frequency. And because we are doing local standard of rest correction for each of the measurements, that all of a sudden shows how big the correction is. So that used to be a fixed frequency, but as you can see, it goes quite a bit, many tens of kilometers per second. And this is a significant correction that you get. If we wouldn't do that, if that would be a straight line, that would be shifted up and down just like this curve, and it would not give you the correct answer. This is also demonstrated by what you have already seen. That doesn't quite work that well for a simple dipole, because the dipole is looking in all sorts of directions. So the correction that I'm doing is only correct for one specific direction, but my poor dipole is looking everywhere else, and I can't distinguish which is coming from where, and so I can't do precise corrections. This is why this is so much shifted here. Anyway, the message that I want to get across, if you dig deeper into things as you progress, think about the LSR correction. Okay, next is a scan of the galactic plane. In this case, it's not a transit scan, not something looking straight up, but in this case we used our 2.3 meter dish, and we went in the galactic plane along the galactic longitude, from the galactic center all the way to around 248 degrees. That's as far as we can get. All the rest is below the horizon for us all the time. Again, you see our nice RFI line interfering, and due to the LSR corrections, it's curved. So this is essentially what you get if you scan along the galactic plane. And one of the well-known and nice experiments is to take that and then evaluate that by looking what is the highest redshift velocity. And you can do that for geometric reasons that I won't go into detail here, only reasonable for this range between the galactic center and 90 degrees galactic longitude. At this point, I would like to mention one thing. Listening to the previous recording, somebody mentioned that there's no hydrogen emission at the galactic center. This is not correct. It's a significant emission, as you can see here. It's fairly bright in hydrogen as well. Anyway, this is the sort of the famous experiment to determine the rotation curve of the Milky Way. Tonight, I don't have the time to go into the exact rationale why you always take the highest redshifted velocity. This method is called the tangent point method, and it's worthwhile looking into that. It's a little bit involved, I have to admit. It's geometry and stuff. I have put a link down below here with one of the many explanations, but this is just one that I would recommend to look at. The main story here is you can determine the rotation velocity and the distance from the galactic center. So the relationship between the distance from the galactic center, shown here, and the rotational speed of our galaxy by just taking two parameters. One is the galactic longitude that you're looking at. This is just where is your telescope pointing, and the other one is this famous maximum velocity, maximum redshifted velocity. So these are your two measurement parameters, and then you can determine R and V. One is the distance from the galactic center, R, and V is the velocity, by these equations. The only thing that you need to have in addition, you need to know what is your own distance from the galactic center, R0. You have to take that from the literature. And what is our velocity, rotation velocity of the solar system, which is 220 kilometers per second. So if you throw in these two parameters and measure that, you get this rotation curve. And the famous story, as you probably already know, is that the velocity remains more or less constant as you go out from the galactic center, which the story is, this is an indication that there's more than just the gravitational force from the stars in a known material, the baryonic material. There must be something else called dark matter. So this is the point where we're getting into fundamental physics with a very fairly straightforward experiment. You have let's say a 2-meter antenna and then scan the galactic plane, and then all of a sudden you're ending up with something that is not known at the moment in traditional physics. So open question. And that's a famous experiment, obviously, which is certainly worthwhile doing. Now, how about hydrogen outside our galaxy? Here things get a little bit more difficult than just using a dipole. And I'm referring here to some excellent work by the late Jean-Jacques Mantoux from France. He has a 3.3 meter dish, very low system temperature. And I'm showing here two of his experiments, or two of his recordings from M31. M31 does overlap with our local hydrogen, so this is a little bit of extrapolation, and M33. So you see essentially the full spectrum of the other galaxy here. Now, this is not so easy to do, and I want to put that a little bit in perspective. First, what Jean-Jacques has done, he's been working successfully but intensely on getting his spectral response flat. So he started out with a more wavy pattern and rising. And he has been working on his receiver chain to get it really, really flat. That is one of the really important success factors, because if you see small variations, you don't want to get fooled by variations like that. Another thing is putting things into perspective with the question, how big does the antenna need to be? And this is a calculation I've done and simulation using simulated antennas of different diameters and asking myself how good a signal from M33 would I get. So the top curve here is calculated for a 3.7 meter antenna, so an opening angle of 4 degrees. As the antenna gets smaller, the signal decreases. And at a 2 meter antenna roughly, it's quite difficult already. So observing electrogalactic hydrogen becomes quite difficult if you go with antennas of less than 3 meters, but it is doable with antennas of 3 meters. And so it's not only Jean-Jacques who successfully did it, there are also some others who did it. It takes some effort, but it can be done. But again, taking that a bit in perspective, if we put the signal from the M33 galaxy, it's here, and this is the hydrogen from our own galaxy. And this is not really a strong position in our galaxy where the hydrogen is really strong. This is where it's strong. This is a 70 Kelvin hydrogen line here. This one is here, and you see that barely. So you really have to take a magnifying glass to see that. So we're talking for the hydrogen in our galaxy, we're talking up to a couple of tenths of Kelvin brightness temperature. In M33, 0.15 Kelvin. So that's just to tell a bit what the challenge is. All right, moving on. Maybe it's a little bit easier to look for something which I put under the title exotic hydrogen. That's something called high velocity clouds. Now, high velocity clouds are what the name tells you. These are clouds in our galaxy where the hydrogen has a very high velocity, higher than the rotational. It cannot be explained by the rotation. And I'm showing here a high velocity line, or high velocity cloud. It's part of the so-called H complex, which is done with our 3 meter dish and 30 minutes integration time. So it's clearly visible. There's a velocity of 200 kilometers per second blue shifted, so coming towards us. And also Joaquin Hiniau from the Netherlands, who unfortunately also passed away some time ago, very successful with the things that he did. He used a 1.5 meter dish and 5 hours integration time. That's the same line there. So it can be done with a small or fairly small dish to detect the high velocity clouds. There are very places in the sky where these hydrogen high velocity clouds can be observed. What is the physical origin of these high velocity clouds? That's unknown, actually. There are several possibilities or theories. One is the galactic fountain, where people say, okay, there has been an explosion, like a supernova explosion, which has thrown out large amounts of hydrogen out of the galactic plane, which is then eventually falling back. Then there's a big halo around our galaxy, and some say, well, it could be condensing halo gas, so it condenses and then is attracted by the gravitation of the galactic plane. Some say it could be also primordial gas clouds which are meandering around and caught by our galaxy, or it could be so-called tidal streams, things which are attracted by a satellite galaxy. So it's not known. There are different theories, and they're very difficult to distinguish. But they make nice observations. So if you want to go after that, that's a bit more involved than our galactic hydrogen because it's simply weaker, but it is quite doable and actually easier to do than the other galaxies. Okay, continuing on the exotic hydrogen, there's something called radio recombination lines. Let me explain what that is. You probably know, at least those of you who have also had some interest in optical astronomy, there's something called the H-alpha line, which is a red, optical red line. Now, in the context of the energy levels of the hydrogen atom, what we know as the alpha line is actually the H2 alpha line because it's a transition between the third and the second excited stage of hydrogen. There's the H1 alpha line, which is in the ultraviolet because the energy difference is much bigger. The next one up is in the infrared. Now, since the energy levels of the hydrogen atom or any atom, as the higher you go, get closer and closer and closer and closer, if you're high up, the energy difference is in the radio regime. So you go from ultraviolet to visible to infrared and far infrared and so on, and then eventually you end up in the radio regime. So if you can somehow get transitions there, there should be some radio emission. Now, how do you get transitions there? When you are in a star-forming regions where there's a lot of intensity, ultraviolet radiation, lots of infrared radiation, atoms can get ionized, so the electron separates from the proton. And eventually they recombine, so the proton catches an electron. So again, from the two separate parts, you get an atom. And this atom can typically be in a highly excited state. And then you have that, what you want to get. You have a highly excited hydrogen atom. And this, again, occurs in star-forming regions, A2, H2 regions. And these radio emissions can actually be observed. Quick look back to Henk van der Hulst. He also mentioned that in his analysis, and he said it can't be observed because of stark broadening. He was not correct in that point. But that was, by the way, it was a long discussion. Can it be observed or there's too much stark broadening and so on? Lots of theoretical calculations, but yeah, it's something that can be detected. So this is a recording of a radio recombination line. It's a H166. So going back here, we're in the 167 to 166 level transition. And this is the emission that we get in the Orion Nebula. That's a star-forming region. What you see here is also a radio recombination line, but in this case from carbon. So you can actually also see other elements there. By the way, we don't see helium for some reason. I don't know, but helium doesn't show up. I have to say, though, that this so far has only been observed with a large dish. And whether it is possible to see that with a dish in the 3-meter range might be possible. Not sure about that. It has something to do with the extension of these excited regions, because you have the large opening angle, and that region may be too small to give you enough energy to observe it with a small dish. Anyway, it's maybe eventually something that one wants to go after. All right, so what does it mean in summary? The hydrogen atom, it's 21 centimeter lines and also other lines that are That's a wide area of observations. You can do the mapping of the intensity and velocity in our own galaxy, and that's easy. I mean, whatever your antenna is, you can do quite something there. If you have sufficient spatial resolution, like from a 1 meter dish upwards, you can certainly do the rotation curve of the Milky Way. It's also easy. High velocity clouds I would consider be doable. We have seen that with a 1.3 meter dish from Genio. So we get a good signal to noise ratio with a 3 meter dish, so that's quite doable. Extragalactic hydrogen, as interesting as it is doable, has been demonstrated with 3 meter dishes, but it's not that easy because of the difficulty to get your baseline sufficiently flat or get it reasonably corrected. There have been some demonstration from various peoples how to do that, and they have been successful, so it's difficult but not impossible. Radio recommendation lines, I'm not sure. It's worthwhile a try to do this also with a smaller dish. So, as you can see, there's a quite big area what you can do with 21 centimeter line. There are two things that I have not covered in this talk because they're really reserved for bigger dishes. There are absorption spectra which you can see. For example, you can see absorption spectra towards Cassiopeia A or the galactic center and so on. And then there's another one which is deep space hydrogen clouds. These are clouds that can also be seen in absorption at very high velocities. But again, the sensitivity of the, let's call the amateur size equipment will probably not be sufficient to do that. All right. All through the talk slides, I have a couple of resources and links here, two more. The first link is to our website. It looks like as if it were in German because this is sort of a German title, but it is in English. That's a series of articles, 4 articles, which cover these things that I talked about in a little bit more detail. It's about what antennas have been used, what the results have been, and so on. It's a couple of years back, so not everything is perfectly up to date, but I'll certainly give you the idea. Then I talked about the local standard of rest. There's a SARA journal article from July-August 2021. And as I mentioned, I have the recommendation and the suggestion to really look into the LSR correction. We also have put some software on GitHub, which you can use if you want to do that. So feel free to download it and use it. And I guess that concludes my talk. Thank you very much for paying attention. And of course, I'm really happy to see your questions and hear your questions. Thank you very much.
Wolfgang, that was absolutely marvellous. Thank you very much indeed for coming and speaking to us tonight. Wow. Gosh, yes. I'm sure there must be plenty of questions that people would like to ask. So who would like to go first?
Wolfgang, magnificent talk. Thank you again. You always put things in a wonderful perspective. Going way back to the extragalactic spectrums that you had kind of different color spectrums, yes. How do you achieve the red on the right on the left diagram?
I have to say these are not my results. These are made by, I took this from Jean-Jacques.
Sure.
And I would love to ask him. Unfortunately, he passed away some time ago. I think what he did, he was using some, I can only speculate a bit here, some of the high-resolution data from that gave him some idea of what it would like. Another possibility is that he was assuming that it would be kind of symmetrical. Typically, on a galaxy, on a spiral galaxy, the typical shape is that you have a higher peak, then a flat bottom, and then a higher peak again, which will be typically kind of symmetrical, like is also shown here. So if you assume it's symmetrical, so that's sort of an extrapolation.
Could you see that with a large aperture dish as opposed to the dishes we might have in our backyard?
Not quite, because it really overlaps in velocity. You will be able to distinguish it a bit better because your beam is narrow, and when you have a narrow beam, you might be seeing more of that and less of this hydrogen line there. But there's not so much of a difference, so you really have to do a bit of guesswork and speculation there.
Just a suggestion.
I'm honored that you're mystified as well. Thank you for your help.
Just a suggestion. This might be a silly idea, but is it possible he might have pointed his telescope so it was just outside of, the beam width was just outside of M31 or M33, and then picked up the Milky Way there, and then used that to subtract from the signal when he was pointed at M31 or M33 to see what was left?
Yeah, I think what you're referring to is the idea that you assume that as you move your beam a little bit, which could work with a with a bigger dish, that your galactic hydrogen remains the same, whereas the M31 will disappear. So you would see a slight difference here. Yeah, that's a possibility. I personally haven't tried that. We do have made recordings of M31 with our 25-meter dish. M31 is pretty big, so we don't have the full galaxy in our beam, so we have to sort of scan it. We haven't paid exact attention to that. Maybe that's worthwhile doing. I'm not sure how good that will work, but yeah, it's worth a try. I mean, the idea is perfectly fine. Just move it a bit and see, under the assumption that the little movement doesn't change your galactic hydrogen, and attribute the change to what you get from the M31. Yeah. That's at least a theoretical possibility, yes.
Okay, is there anybody else like to ask a question?
Yes, I have a question, Wolfgang. This is Adrian. When you were discussing the high velocity hydrogen clouds, have you been able to observe the high latitude high velocity neutral hydrogen clouds, which were entrained within the Fermi bubbles?
Actually, I don't exactly recall. We have done quite a number of observations of the high velocity clouds in various complexes, but I'm not sure where we looked at those. I would need to go back to our recordings from that time when we did that.
Okay. Just curious.
Yeah,
there was a recent presentation, the Green Bank seminars that they have. There was a recent presentation of observation of those. Of course, that's with the 100-meter intent, so still a little bit larger than aperture than what you all have. But I was just curious if you had been able to resolve those. That's the only reason I asked.
Yeah, one of the things that you, if you're interested in that you may want to look into, there has been an extensive work on high-velocity clouds by a gentleman with the name Tobias Westmeyer, and he did that with the Effelsberg telescope. I think he did his PhD thesis on that. So if you look for the keywords high-velocity cloud and Tobias Westmeyer.
Okay, thank you. By the way, that was a fantastic, excellent presentation. It was very, very informative and enjoyable. Thank you.
Thank you.
Okay. Have we got anyone else? Anyone else? Sorry. Steve, were you hoping to say something? No. If you are, you're muted. You're still muted. Still can't hear you. Oh dear. Oh well. Now you're unmuted, but sounds like you're still quiet. If you've got a question, you put it in the chat. I could read it out. While he's doing that, is there anybody else in the group? No. One question I would like to ask you on an unrelated topic, Wolfgang, is there any member of your team who, with experience in interferometry, that's going to come along to the British Astronomical Association Day Conference in October? Do you know?
I would need to ask. I know that I personally probably won't be able to make it in October, but there are a couple of people involved. Somebody, by the way, whom you could ask is Thomas Telkamp from the Dwingeloo team, because he's I would say, the main brain behind the VLBI experiments that we do, and we can look into that for the October time frame, whether you can do it.
We were looking for somebody who might be able to give a sort of keynote on interferometry for us.
Yeah. Well, the interferometry work that we ourselves have been doing was a very simple interferometer. It's a 3-element interferometer, essentially for lab courses for the university, which Vanessa from our team did. And then we have the fantastic ideas and work from the Dwingeloo team together with us, doing the first time VLBI, where we really had independent telescopes 200 kilometers or so apart, where we did interferometry between those two. So these are the two things. At the moment, we are actually quite heavily working towards doing some more interferometry work. We also have a couple of things done with two of our smaller dishes, not VLBI, though, so that we're really phase tied together, so that we're on the same location and at the same clock source. Also tell something about that. Let's take that offline and see what we can do for October and who could do that.
Marvellous. Thank you very much indeed. Talking of which, just so before we move on about that, I wonder if Steve has now put something in the chat. Let's have a look. So he's asked the question, is the data format you use for your collections the FITS format?
The data format for what, please?
Your collection, the FITS format. I think he's mixing up radio data collection with a photographic collection, I think. So I guess he's asking ultimately what data format you use. You said you were using professional data formats. For your data.
The data format that we use for the spectral data for the hydrogen data and other spectral data like OH masers and what other masers, that's called FITS. And
so it is the FITS format. So Steve was quite right.
One have to say though, FITS at first is a very general expression. FITS was originally developed for storing pictures, and there is a scheme that has developed in the radio astronomy to use that with certain information in the header describing spectral data. And so we use the FITS format that is sort of the commonly used between the different universities and observatories to store spectral data.
Oh, brilliant. Thanks very much. And my apologies to you, Steve, for suggesting that you'd made a mistake there. You clearly hadn't. I'm the one that's made a mistake. Sorry about that.
I mean, there was just a quick comment from Steve saying FITS is a journal format for all sorts of scientific data, and that's perfectly correct. It's so generic that you can put in almost anything, but you have to agree if you want to do spectral data in something, what is the minimum information that has to be in the header so that you can correctly interpret that. And the background also is that everybody and his brother is using the same programs to work with the spectral data. And that's how you read the data. So you have a common format and you read it into these programs where you do all the baseline corrections and the calibration stuff and so on. So it's more, let's say, a community standard which is based on FITS, but specifically not adapted, but specifically used for spectral data.
Marvellous. Thanks very much. Well, that is very kind of you indeed again for coming to speak to us this evening. I think I, for one, have definitely learnt a phenomenal amount, and I'm sure everybody else feels the same way. So can I ask everybody to give Wolfgang another clap, please, to thank him for it.
Thank you.
Thank you very much indeed. Having mentioned the British Astronomical Association's Radio Astronomy Group Day Conference in October, we have Paul, who happens to be the director of the BAA RAG, on the line with us tonight. Paul, would you like to say something about that meeting, about people, how they can get involved, and in particular, we wanted to ask people, I understand, whether they would like to give a talk, present a demonstration, and other ways they might want to be involved.
Exactly that. Yes, the BAA are sponsoring this meeting, and for members, it's only £10, and that includes all your food and drink and cake on the day. It's only £20 if you're not, so it's quite a low cost to the individual, thanks to the BAA. Okay, we're going to have some demonstrations, people showing what they're doing at home. Now, for radio astronomers, that's not going to be that easy for some if you've got a large dish that's not transportable. But we are setting aside a chunk of the day, maybe a quarter of the day, for H-Line observations. So if there's anybody on the call that thinks they'll be at the meeting on the 3rd of October at the Sherwood Observatory, and you want to, or you feel that you would like to share what you've been doing in terms of either a presentation or lumps of hardware you want to talk about, then that would be just fantastic. That would be so good. We've got one academic speaker so far, but we're wanting to reserve most of the time at the conference to the amateur community. This is the first meeting the RA section have had for quite a long time, face to face. Obviously, we had the European meeting last September, but apart from that, the local UK meeting we've not had. So, if anybody would like to share, that do contact me, and we can give you a time slot. And as Andy's already said, what we would really like is somebody to talk about phase array, because there's a number of people that have been experimenting, putting together telescopes that are beginning to think about the next step. So phase array with simple, low-cost components would be a great talk. Okay, I'll stop there. I don't want to take up too much time, but yeah, thanks for that, Andy.
Pleasure, thank you. Wolfgang, say thank you very much again for this evening. We'd love to have you stay with us for the rest of the evening if you want. On the other hand, if you have other things that you need to do and you need to leave, we won't be offended. So whatever suits you best. You're extremely welcome to stay around.
I'm happy to stay on and enjoy.
Well, that's brilliant. That's fantastic. Yeah, I didn't want you to make you feel that you were forced to hang around. Paul, in that case, I'm going to carry on with yourself. Would you like to talk about what you're doing in Hydrogen 9? Because I know you've been desperate to tell us a bit about it over the last few months, but couldn't make the various meetings.
Yes, I'm saying I'll probably have more slides next time, but progress has been made. Wolfgang referred to the website at Astropelia, and that was my first port of call when I was wanting to design the waveguide. For those of you that don't know, I'm in the process of putting together just an 85 centimetre XTV satellite dish, and I've characterised that, having discovered that they're not a part of a sphere. I know, basic thing, isn't it? I never really thought about it, but it is a bit of a parabola, of course. Anyway, I've characterised that, and that's all good. Using a paper I found on Wolfgang's website, I managed to build the Cantana, so that's done. I've been playing around because it's been so cold to do anything in my workshop. I've been playing around with software to read my inclinometer, and I've got that sorted out now as a lash up on the bench. I've not got the print boards made yet, so that's done. I've got the drive software going to drive the dish. The thing's mounted on a pair of 12 volt 5 amp motors because it came off our motorhome when I bought it. So I'm going to it will be steerable, but I probably won't do much of that to start with. I just want to get the thing pointing at the sky and doing some drift scans. So yeah, it is progressing. I've finished the mechanical construction that will be the mounting point for the mounting table for the dish, and I think I've got all the bits now. I haven't yet characterised my my waveguide with the nano VNA. I haven't started playing with that yet, but probably before we meet next time, I would have had a chance to do that. Once I get my head around how to use it, I've not done that yet. So yes, that's me, what I've done, what I'm planning, and I'll see you again next month. Thank
you very much. Thank you. Has anybody got any comments for Paul or anything they'd like to say? No? Okay. Right. Next, I would like to invite Dave Bracey. Dave, you wanted to talk to us about a couple of bits and pieces, and your comparisons that you were making using easy radio astronomy and some dish modifications to see if you could improve the quality of your galactic plots. Is that something you're still able to talk to us about this evening?
Andy, yeah, definitely. Okay. Yeah, I'll do so. Nothing to the same degree of professionalism, of course, as Wolfgang. I'm very opposite end of the spectrum, very, very much a newbie in all of this. But yeah, I've tried a few things out, and I thought I might share with them to you. Apologies to anyone if many of you will have done all this before, but I thought it might still be interesting to share this. So yeah, okay, all right. I'll share my screen and all that stuff. Let's have a look. Let's share with screen. Screen 1, allow. So hopefully you're now seeing one screen, yeah?
Yep.
And
absolutely.
Slide. Okay, hopefully I'm just checking that you are seeing what I think you're seeing, because I've got two screens running here, and the other screen is just showing the next slide and stuff like that. So hopefully you're just seeing one screen. But yeah, okay. On that basis, yeah, I'd say I've been using Ezra for a few months now. Brilliant fun, fantastic. Really, really enjoyed it. And Ted's made a superb product here. Really wonderful. And yeah, so I've produced produced a few maps. You can see my little one here. Very pleased with it. Obviously, there's things I need to improve my reduce my increments of movement, because it's rather steppy at the moment, isn't it? And that's the obvious thing to do, I thought. But Before that, I've noticed other people using variations inside of Ezra which show really good promise. I mean, Andy, you've been doing one of them, increasing your the number of days that you've been gathering data for on each declination, and your results look really great. And there's a few other things you can do with an Ezra too. And so I thought, well, before moving on, I thought I'd like to use some of those to develop my next approach. But the problem is that evaluating these things, it's very subjective, isn't it? You know, you're looking at these images and you're squinting at it and thinking, well, is it better or is it worse? You know, am I seeing more detail or not? And at the same time, it's very time consuming doing all this. You can just take weeks, months to produce the full map. So I thought before launching into my second round, as it were, I thought I'd do some experiments to try and quantify and compare some of these options, and then sort of try and pick what I think is the best combination, to make the best use of my time. So I'll move on to the next slide, as it were. Yeah. So in order to do, I thought I'd try and get away from the subjectivity. I thought I'd try and narrow it down. So just pick 3 parameters to look at, and the first parameter I wanted to look at was comparing single day observations, so just 24 hours, which I have been doing, against letting Ezra collect data over several days, 2, 3, 4, 5, and I think Andy's gone way beyond that. So that was interesting. I thought I would look at dish diameter too, and that's very interesting what Wolfgang was talking about with his comments about that. So that was second parameter. And then the third parameter I thought I'd look at was, I noticed within Ezra there's the option to go from 8-bit to 10-bit, or I think you can go even beyond 10-bit if you want to. So I thought, okay, let's see what that does too. Now, how can I assess the changes or the improvements? And again, I thought I'd narrow it down just to look at 3 Ezra plots. So the first one is the classic one that Wolfgang was showing of longitude against velocity. Look at that one. I thought I'd look at the galactic arms plot that Ezra produces. Wonderful, absolutely love this one. So have a look at that. And then third one, another plot I really, really like in Ezra is the EasyCon 87, where it's showing Doppler against time. So this is 2 and a bit days of data, so you can see 2.5 rotations. But as I say, I really love this, because this to me, this is showing me what giving me more of an idea as to what the antenna's really is seeing as time progresses. But I know that Ted's been working on an enhancement to this, where instead of showing the 2.5 days spread out like this, he integrates it all into one day, into one plot, which you're seeing down here. So this is now showing Doppler against right ascension, and all three of these plots are combined are integrated together to form this plot. Now this is, as I understand it right now, this is beta. This is not in Ted's standard issues. He's not supporting it right now. But Ted very kindly let me have a look at the beta version of this and give it a go, and I've really appreciated that, because it's been really useful. So okay. So moving on. In order to try and make the best comparison I could, I thought, okay, I want to simplify as much as possible, keep it apples to apples, to try and get some of the subjectivity out. And so I've just picked one position from a dish, and I picked 32.5 degrees declination. just simply because I thought it looks an interesting one, but no more than that. And I thought, okay, I'll keep my integration times constant to around 30 seconds. So I'm not changing that. And then go through those three options of looking at collection time, dish diameter, and the bit rate, bit collection rate. So what did I see? Okay, so this plot here. This is looking at in the top. I hope you can see my pointer. Up here you can see the EasyCol Doppler against right ascension for 1 day, and again because I've zoomed in here on the I think this is approximately looking at the Cygnus area of the galactic longitude. So zooming on this one, and I've blown it right up. I've got 1 day, 3 days, and 5 days, and I've compared them and said, okay, what difference does it make when you increase the number of days? So, as the first thing I noticed, which is the one thing, is that as the days progressed, the graininess, sorry, I don't know if that's a word, but does start to improve as the days go on to some extent. You get the most improvement on 3 days, and when you get 5 days, not so much of a change happening. One quite noticeable change is that there's separation between arms. You can see it's on day one, it's still a little bit blurry between the two, but as the days go on, you start to get a more clearly defined separation, particularly on after 3 days. And 5 days maybe there's some improvement, but I really like this. I thought this was great. And again, what I've called the tail here, this is in time. This starts to reduce as you increase the number of days, so losing some of the noise, as it were, as your integration time increases. And then also another interesting thing is that look how the background is becoming darker as the days go on. So I'm assuming this is the signal to noise ratio improving as time goes on. So yeah, it does make a difference when you go from 1 day to 3 days, 5 days, and properly going on beyond that. I mean, I sort of didn't want to spend months on this, so I stopped at 5. But yeah, probably going on, maybe you'll get some more improvement. Then I looked at the EasyGal 510, which is the galactic longitude velocity plot. Again, I've got day 1 on the left, and then 3 to 5, and I'm looking to see what changes there are. And the changes are subtle, but they are there. So you can see when you go from 1 to 5 days, there's this sort of darker area between the arms. This is slowly starting to separate as time goes on. The area outside of the outer arm, this is as time goes on, this is becoming darker and reducing. So the noise beyond the outer arm is reducing. Didn't see much change on the main arm, but okay, things are happening as you integrate more and more days. And then this is the EasyGal 510 plot. So looking at the image that gives you the arms, and looking at again, I've got 1 day, 3 days, and 5 days. The changes on this one, they're pretty subtle. There's not much effect on the main arm. Maybe this definition is increasing slightly, but not that much. And the outer arm, outside the outer arm, well, maybe it's improving a bit, but nothing drastic. So okay. So my conclusions with this were that multi-day data collection, it definitely does make improvements. Probably best seen on the Doppler right ascension plots. And for my test results, at least, I think I got my best improvements on the 2nd, 3rd day, and it may be that it's diminishing returns after that, but I didn't go much beyond 5, so I can't be that sure. So yeah, I was pleased by that, and I thought, multi-day, it does make an improvement, and I shall include that in my next in my plan for my next my next stage. So then I thought, okay, now let's go on to dish diameter. And I have built an extension to my dish. So this is my original dish. This is 1.5 meters. It's home built. It's a geodesic design. I was quite pleased with the results it gave me. I've made some careful measurements of the shape of it, and it's pretty close to a parabola. So I was happy with that, as best I can manage myself in my home workshop. But I wanted to try going a bit beyond that. So, but at the same time, this is just about manageable. I can carry this in and out. But going bigger, things rapidly spiral out of control. So I came up with a design where I bolt on extensions to the outside of the dish. This is one of the extensions up here. And these are built in quarters, so all four are bolted on here. And I did the best I could to approximate to the parabola for these outer shapes. It's not flat. It's not a perfect parabola, but it's I thought, okay, it's the best I can do without going crazy. Let's see what it does. So same thing again as I did with it. I've standardised here on 2 days. And what did I see? So again, looking at the thickness area of the Milky Way. So the blob, as it were, of the main arm, well, it's slightly small. The differences are subtle, very subtle. But you look at it, there are differences. The blob is a little bit smaller. The tail area is reduced a little bit, and I've got an increased colour contrast. This is the 1.9, that's the 1.5. So maybe my signal to noise ratio has gone up a little bit, but not a lot. And okay. Looking at then I looked at EasyGale 570 and EasyGale 510, and well, I have to be honest with you, didn't make any difference really. I can't say to you, I've got any big differences, because maybe there are some subtle differences. Separation's a little bit better, maybe down here, but nothing dramatic. But it didn't make it worse. Anyways, that was something. And maybe my signal to noise ratio has improved. But one thing I did notice when I was doing this is that I had quite a. This is an unexpected result, but from with the 1.9 meter dish, my peaks here on the main arm are somewhat larger, or quite a bit larger actually, and I didn't expect that, because as Wolfgang said, your dish area and your observed area should cancel each other out, and I'm not seeing that. And I thought, oh no, maybe I've defocused it a little bit. Maybe my extensions aren't as parabolic as I thought, and so although my collection area has gone up, maybe the area that I'm viewing hasn't gone down enough if I've defocused it. So I got a little bit worried about that. But I then found this website, this Leiden Argentine Bonn lab survey website, which we've got over here, where I think this is 25. I think this is 25 meter dish data, and you can input your position, so where you're looking at, and I hope you're not seeing what I'm seeing, but right where I'm looking, there's a field here where you can put in your half power beam width.
Yeah, Dave, you can actually. So forgive me. You can actually
split out I think it's a simulation from their data of what they would have seen. And so I plotted here the 10 degree beam size against the 7 degree beam size, which is what I think I've got. And well, they're saying that there will be a slight difference, and that my 7 degree, or 7 degree, which is approximates to 1.9 meter dish theoretically, maybe that will be a little bit bigger. From what Wolfgang said, maybe that's not true. I don't know. But I saw that and thought, well, maybe I'm not so bad. These are my results, by the way. These are their simulated results. But then I thought, well, okay, to check how bad my extension is, maybe I can measure the half power beam width by doing some solar drift scans. So I pointed the antenna in an area where the sun's going to track across it, and let the sun move across the dish. And to collect the data, I used a program called Total Power put together by Mario Armandi. And I've seen Edouard Moll using this. And all it does, you give it a frequency to look at with a bandwidth. And I used 1423 because I knew that that's the reference, the frequency I use for my reference signal. So I knew there wouldn't be any hydrogen signal there, even though the sun was well away from the Milky Way at this point. And then I processed this data using I'm going to horribly mash up German with this, but some Kiel-Rona Kiel-Rona method. And there's a website where they describe this quite nicely. And what they do is they take the logarithmic power that you've been recorded by the Total Power program, convert it to linear power, subtract the cold sky power, and then look for half and find the half point between the two, and then you can then project down onto the degrees that you've been scanning over and see what your half power beam width is. And well, the blue line is my 1.5 meter dish, and I've apparently saw a 10.2 degree half power beam width, and that actually compares surprisingly closely to the theoretical value of 9.8. Then I did the same thing for this is the next day. I put my extension segments on, let the sun traverse across, same as before, and looked at what the half power beam width is, and well, it is less. It's so maybe my defocusing wasn't quite so bad. I'm measuring 8.6, and theoretically, according to the K lambda over D value, you'd expect 7.7. So, well, okay, maybe it's not quite as bad as I thought. But then again, maybe the change to the galactic plots are too subtle, just to be noticed in just one segment. I don't know. I'm gonna persevere with this and see what I see. But yeah, okay, nothing dramatic. I'm not expecting anything dramatic, I suppose, is the headline from this, but I'm hopeful. Then, okay, this is an interesting one. Then I tried the 10-bit, 8-bit and 10-bit comparison. And there's a setting, in the Ezra command line, you can ask it to record in 10-bit rather than 8-bit. And I did have to make a change to my integration quantity in order to maintain my 30-second integration time. Okay. Okay, so these are the two results. So on the left, got my 8-bit. On the right, 10-bit. And look at the difference in the separation between the two arms. Look at the difference in the noise outside of the outer arm, how that's reduced a lot. Look at the difference in the colours, in the scales, which I'm taking to be signal to noise ratio. Definite improvements here. So I think this one is really, really working. Looking at the 570, the galactic arms and the sun. This one shows some real changes. So you get these on 8-bit, you get these, the main arm looks really dotty, doesn't it? When you look at it in 10-bit, look how much smoother that is. Really, really nice. Look how the noise outside of the outer arm is really cleaned up. My outer arm's a little bit smaller and tighter. I'm taking that to be a real result, but very, very pleased with that one. This one is a very nice feature. And then, this is the velocity against right ascension. Again, 8-bit here, 10-bit here. Look how much smoother this is. Look how much there. You can see that the outer arm has tightened up quite considerably, much less noise. Some reduction between the arms, and look at the intensity scales too. So again, the 10-bit has got a much larger better intensity scale. So yeah, I think this is really nice. So then I'll put it all together. Okay, so let's compare how I have been recording things on 1.5 meter 1 day and 8-bit against, let's say, a new system of 1.9, 2-day and 10-bit plots. How would the two compare? And I think that the 510 plot is on 10-bit 1.9 is much better, with much better separation, much less noise, much bigger intensity scale. So I really like that. Here again is the EasyGale 570. Again, I think a much nicer plot doing this. Obviously, quite a bit more detail doing this. And then this is the EasyCon Doppler right ascension plot. Again, with much nicer, much clearer plot. All the graininess has disappeared. It's smoother. The outer arm's smaller, more tightly defined, much bigger intensity scale. So I think this is really worth doing. There we go. So my conclusion, probably marginal gains. I think for my results, I got the best improvement on the second and third day. Dish diameter, gave me maybe something, but that's probably debatable. Maybe I've got some more work to do on that. And but 8 to 10-bit, that's for me, that's the one. But the only problem is that I've got a lot of 8-bit data now, but you can't combine. It doesn't seem like you can combine the two. So I've just got to start again, right from the beginning again, with this new setup. Can't combine it with any of my existing data, but never mind. I think it'd be worth it in the end. I've got to come back in a few months and show you what I've got. So there you go. That's it. I'll just stop sharing now. And any comments anyone may have, very interested to hear them.
I think that was really interesting, Dave. Thanks very much for that. I got to say, personally, I'm really jealous of how good your plots are, with or without the modifications. So to suggest that you got inspired by mine is pushing it a bit, I think. I'm inspired by yours rather than the way around. I wonder a bit whether you talk about the benefits seeming to be less the more days you added. I wonder whether it's, I don't know, is exponential the right word for it? Where you get a lot of benefit initially, but then so the law of diminishing returns as time goes on. I mean, what's the right word for that? I wonder.
Well, I don't know, Andrew. I've only done up to 5 days. I know you've gone a lot further than that.
Yeah, well, I've gone up to 28 days. It's what you do with a radio telescope when you've finished a mapping exercise and you wonder what you're going to do with it now.
Yeah.
Just go back and do it again, except with longer time periods.
Everything should take years, then, doesn't it? When you really got to...
Well, I can't find an excuse to keep it there.
I don't know. I've got to pick something. I probably can't go to the months like you've done. But yeah, don't know. If you it'd be interesting to see your month results.
Oh, there were just been a comment added in the chat to say that signal to noise ratio improves as the square root of integration time. So I think that fits in with that's from Steve there. No, from Ted, is it? No, from Steve. Sorry. So I think that fits in perfectly with your experience there. That you get the benefit exactly as Steve's demonstrating. You get a lot of benefit initially with less as time goes on. Yeah. The other thing, just to finish off from my perspective, Ted's making a suggestion, I think, for things that you can do in in Ezra. Maybe you get him to chat in a second, but I'll just finish off by saying I'm just wondering whether this group should officially introduce the term a Dave Bracey graininess index as a way of describing the quality of plots. And we could perhaps have it from 0 to 10, maybe. I don't know.
No, okay, I don't. Yeah, okay. I don't see mine as being particularly good, but yeah, okay. Thank you.
Your graininess index, anyway. Anyway, Ted, you what was that you're posting there in the chat? Do you want to talk about it a little bit?
Well, you can't complain that EasyCon doesn't have enough parameters on it. It keeps ballooning with all kinds of new ideas. And one of them is, as we sweep, you're doing drift scans here, so no motors. So as you drift scan, as you drift through the viewing of the galactic plane, we can talk, it's changing in galactic longitude. So we're looking at different parts of the pizza for the galactic plane, and you're picking out particular angles of galactic longitude. But what's the resolution of that? Is it exactly at 80 degrees? Does 80.1 count? Does 80.2 count? Things like that. And so I have a parameter in there to open and close that window, and the default is probably pretty big, just so you get results right away. And what you might do is close up that nearness parameter to filter out and only use and only accept data that is closer to one of your target galactic longitudes. That's kind of described in one of my videos. It must be the GAL video. So good luck and talk to me about that. But
okay, Ted, we'll do. I'll go.
Just to give you another parameter to play with.
I have a question. I'm a little bit right. Oh, Steve just more or less put on the chat exactly what I was going to ask about. I was a bit confused between the 8-bit and 10-bit plots, and so I was just curious if RTL SDR is the receiver being used. I believe that has an 8-bit A to D system, and so I was just curious how you can extend that to 10 bits. So I don't know. Maybe Ted can explain that.
Different parameters here. Different parameters. The 8 and 10-bit has to do with the number of frequency channels, frequency bins that we have in our graphs, which makes your files bigger. If you go from 2 to the 8th, which is 256 frequency bins across your spectrum collections, and if you go to 10, now you're up to, I guess it's 1024 frequency bins across the spectrum. And that's independent of what you're speaking of, which is the amplitude resolution of the SDR.
Okay, that answers that question. And so the
let me type in the parameter to the chat so we know which one we're talking about too. I gotta go find it. Anyway,
I had another question in regards to the extension to the dish that you made from the 1.5 to 1.9, and that is that you're changing the FD ratio of that dish.
Yeah.
Yet your illumination might be remaining the same from the same cantenna, and so I'm just curious what effect that might have had on some of your results.
Yeah, so my FD I think went from 0.37 down to 0.3, and yes, quite right. The cantenna exactly is the same. I just naively changed it without worrying about any of that. Maybe that's another improvement, a further improvement I could make to try and sort that out.
And then one more question. Would you describe as noise on the tail end of some of those plots for the arms? Just exactly what do you mean by noise there?
Oh, okay. All right, let's go back and show those. So it's this area. I'm not sharing, am I? Sorry. Let's go and share. I think this goes back to what Wolfgang was saying, that you're talking about this change here, aren't you? So I've got some reds running out here and not there in this one.
Right.
So I was assuming, and correct me if I'm wrong, that maybe this bit isn't really here, and that I should be seeing something more like this. That's purely my assumption. Don't know. I was happy to be staying correct, because I noticed that in Wolfgang's presentation that when he changed from the dipole to the dish, that everything sort of contracted and tightened up. And so I was just making that assumption that this is noise, and the same thing applies to the separation to these red area between the arms. Is that real or not? I don't know. I'm assuming that it's not really there, but happy to be told that it is really, and I should be seeing this.
Well, I will believe you have some influence from the algorithm, how you actually generate the pictures. One has to be a bit careful how the different data dots are then combined into the picture. There's certain algorithms how you generate these, and that can have a certain influence. So it's a little bit difficult to interpret this without knowing the very details of the image generation.
Okay.
Would you expect resolution to improve with integration, or just a signal to noise ratio?
Well, theoretically, you would only improve the signal to noise. I mean, the resolution, spatial resolution, is truly defined by the beam width that you have.
Yeah, well, that's what I was thinking. So I was just that's why I was curious about the being called noise in terms of what was being presented, and perhaps not just the performance of the software that was being doing the integration itself. Okay, well, thank you very much.
Ultimately, my plan to get a better feel for that. I'll just share again if you don't mind. So right the slide right at the beginning. Let's go back to the beginning. So this slide here, okay. Yeah. So what I've done, I've overlaid my data on top of a plot produced back in the 1950s by I'm sure Leiden. Again, I'm very sorry if I don't pronounce this right. Kubchik. This was done with the 7.5 meter Wartsburg array, and under here you can see this galactic plot, and I think it's the only professional one that I'm aware of anyway. So this is mine. Underneath you can see what I'm assuming to be the professional data, and so I'm hoping that you can see on this data that when you move outside the outer arm, for instance, or between the arms, all the dark areas, they sort of disappear around here, and it becomes much lighter. And so I'm assuming that that's why, and again, outside of the outer arm, it all starts to turn the density seems to drop off quite substantially, and so that's why I'm assuming that that the blurring between the outer and inner arms and blurring outside the outer arms isn't real. That's my only assumption. It's based on this Leiden data. So yeah, happy to be corrected on that.
Do you want to put that plot back?
I'm not sure that Ezra does the correct radius there too either. So all of this should be re-examined.
Yeah, but if you put your plots back there, Dave.
Oh, okay, sure. Okay, I do. Which one do you want to see? You want to see that plot? I do
No, the one you just put up.
the original. I do have the original one too.
No,
without my stuff on
the
top.
overlaid one that you put up. Put it back again.
Okay, all right. Let's do that. Sorry for bumping around here.
No, not at all.
And so on the plot you're about to put up, I'm a little worried that you're trying to match radiuses with their radiuses. Okay. I'm not convinced Ezra does it right, but it's fun to get results.
Yeah. Okay, and you're commenting on the position of my outer arm and the laden one, yeah?
Yeah, if you put it back, the slide you just showed a second ago.
Are you seeing that?
Not at the moment. You have to share your screen.
Oh, maybe I'm not. Oh, I'm sorry. I thought I was chatting away and I wasn't. I didn't press allow. That's why. So apologies for that.
Right, I would say that you are not the first person to experience this. We're all go there. I did some astrophotography before I did this radio astronomy. At least I did radio astronomy many years ago, quite unsuccessfully, but more recently when I was getting more successful. And I learned a brilliant technique in astrophotography, which is if you go onto Photoshop, you can actually distort the image. And I discovered if you distort the image properly, you can actually get your arms to line up with the professional arms quite well. But I would hardly say that's necessarily the most professional way to get an accurate plot, though. One of the other questions, but on a more serious note, one of the questions I have wondered is whether there are the sort of light arms and the dark arms, aren't there? So you get, in a sense, it depends what you mean by the arms in the Milky Way, in as much as whether you're talking about, optically, you're looking at the stars, but in fact the hydrogen that we are getting data from is actually located not where the stars are, it's located in the spaces between the stars. So actually the hydrogen arms are in the locations between the optical arms. And I always wonder how much these professional data that we're seeing are using those light arms or those dark arms in what they display, and how that then matches up to what we are demonstrating there in the Ezra plot.
Yeah, it's a good point. Although what I would say is that this what I'm showing here, this is the Leiden stuff. This is H1 data.
Oh, okay, so it should be the same, shouldn't it?
Not stars. No, this is H1. Yeah.
What would you have thought, Wolfgang? What would your be immediate thought to the differences in the location between the arms that we're producing on our plots versus ones in this professional data?
First of all, I mean, that's a fairly old picture, and of course, it's how accurate is that. It also is the interpretation of velocities versus the distance that comes from the assessment of the highest redshift data, and it's without knowing the details of how these pictures are generated. It's kind of difficult to tell. In general, I would be careful. I would be careful of over-interpreting that, because there's also a dependency of how you generate the pictures. I just mentioned the algorithms that we use. Also, you may recall the pictures that I had shown, both from the transit and from the galactic plane. The way these are done is you take single data points and then form that into a picture. So what you essentially do is you have a non-uniform distribution of data points, and you generate that into a picture which consists of pixels with equal distance. And the algorithm that's behind that can introduce artifacts. And if you play around with parameters, you can actually see that. I'm always hesitant with over-interpreting the data there.
So it seems to be that the conclusion there, Dave, is that the original data might be wrong, the way they plotted it might be wrong. From Ted, we've learned out that Ezra might be getting it wrong, or just overall, all of us are just interpreting too much into it, or Andrew's come in with Photoshop and fiddled around with the location of the arms anyway, so they're completely in the wrong place.
Yep. Yeah. I mean, the more processing you do into things, the higher is the danger is that you're creating artifacts. Same thing happens, by the way, with baseline corrections. If you do a baseline correction and you overdo it, you are creating galaxies which are not there. So always be very careful, and when you process data, when you do corrections, that inverted commas corrections, or just alignments of the data, in every step of that, you can create artifacts. And one way of actually determining this is if you play around with parameters which influence the picture generation. If you see a change there, it's not real. It's just parameters that change, but there's no physical reality behind it. And generating the pictures is something that we do for our eyes and for a better understanding, because we are visual people. But if we play around too much with it, we might be over-interpreting the physics behind it.
You know, I think the best demonstration of the problems with the way things are displayed, and I keep going back to astrophotography, but you know, if you take a picture of almost any galaxy, it comes out red. It's because it's highly redshifted compared to us. But you know, there's something most people don't like, looking at a picture of a galaxy that just looks red, with slightly redder bits and slightly less redder bits. What they want to see is a few blue bits and a few red bits, so we change the colours. And there's this great thing in Photoshop called replace colour, which is you select a colour and press a button, and now you can use a slider to change the colour around. But of course, it now has absolutely no relationship whatsoever to the original data. You certainly couldn't make any scientific interpretations from it. However, you can say that you're seeing hydrogen clouds, you can see the spiral arms, you can see some structure, and I wonder sometimes whether that's what we should be happy with. You know, the amazing thing that we can demonstrate the spiral arms of the Milky Way, that we can show that we can pick up hydrogen, that we can demonstrate dark matter, that we can weigh it and get results that are surprisingly close to the professional data. And maybe sometimes we're just trying to do too much, maybe sometimes. But that's just a personal thought. But anyway, is there anybody else that would like to make any comments on what we've discussed so far? No? Okay. Right, Ted, you've been talking. Is there anything that you'd like to talk about tonight apart from what we've done?
No, thank you. I'm just exhausted by all these marvelous presentations. I think this is fun.
It has been a great night tonight, hasn't it? Mind you, it's a great night every night that we do these meetings. But it seems to be getting better and better every month. Okay, well, thank you very much then, Ted. Who else we got on the list? Oh, we've still got a load of people on here. Heather, what would you like to talk about?
How to find the microphone button? I don't have an awful lot to talk about. I think I talked an awful lot last month, and no, I haven't made much progress, unfortunately. So, yeah, but nothing really to report.
Yeah, well, there's certainly no obligation to talk about anything in any of these meetings, and you shouldn't feel like you're missing out giving something. It's only if people have got something they'd like to talk about. Okay, who shall I go to next? We've got Francesco here. Hi, Francesco. Again, you're more than welcome to anything you'd like to talk about relationship to hydrogen line radio astronomy, whether it's something you want to present that you're doing, or questions that you'd like to ask, or comments that you'd like to make. But again, don't feel any obligation to talk if you don't particularly want to, but you're very welcome to do so.
Hi everyone, do you hear me?
Yes, indeed.
Okay. I'm absolute beginner in this hydrogen listening. First thing is building my receiver, my radio telescope receiver, and at the moment I am bringing my parabolic dish dish, 1 meter and 20 centimeter dish. I'm not yet finished, but at the moment I can show you. Wait a moment, please.
Yes, please.
Ah,
Oh, wow.
I take a little distance. Sorry.
Have you 3D printed that?
Yes, every hexagon is singularly printed and then screwed together with these bolts. It is 1 meter and 20 centimeter diameter. With FT ratio of 0.6. But if I thought if I increase the two external rings, I can reach 1 meter 8 with FT of 0.4. The problem at the moment is how I can make it reflecting. I think to use a metallic net, or I saw there is a Faraday material, Faraday screening material is, but I must decide what to use. This is.
Well, I know that people have used both of those things with great success. The only comment I would make is you have to think what you can actually successfully mould to the shape of your dish. So I mean, there seems to be most people quite like the sort of metal netting, but you need something that's pliable enough that you can easily sort of tap it down so that it gives you roughly parabolic shape. Although if you work on a 10th wave, that would give you a 2 centimeter variation without any problems. If you go for a 20th wave, then you could have 1 centimeter variation. So this doesn't need to be super accurate, whatever you do. Plus the hole size can likewise be of similar sizes as well without any major problems.
I think it's pretty accurate because I used Fusion 360 to design the dish and then printed with my Fuchsia printer. I was limited by his plate is 223 for 21 centimeter. So every hexagon is a size of 9 centimeter. Is enough to be printed on my machine.
Yeah, my apologies. I wasn't commenting on the tolerance of your hexagons. I was commenting on the covering that you put on it, and whether that how well that needs to be able to mould to the surface of your hexagons. But of course, if you want to keep that sort of same quality level in terms of accuracy, then you want something that can mould very precisely down onto the hexagons, i.e. it can be tacked down around the edges and give you a very nice parabolic shape. I don't know, does anybody else here have a preference on whether they would say a Faraday fabric or metal sort of chicken wire type netting was better? Or I know Alex at the moment is tend to go for mosquito netting, isn't he? It tends to go over doors and windows.
Andrew, I used an aluminium mesh.
All right. Yep.
Which has got a 6. I think the hole size is about 6 mil by 4 mil, and it forms very easily. You don't have any problem whatsoever. An advantage of mesh too is that when it rains, it doesn't. water doesn't collect in it, and perhaps more importantly, when the wind blows, even with my 1.9, I had 30-mile-an-hour gusts out there yesterday. I'm in a more sheltered area, so I don't think it probably wasn't 30 mile an hour, but there were some quite big gusts, and it had very little effect on the mesh, whereas maybe a fabric might have, the wind loading might have more effect on it, and I think that's quite a important parameter. So you can use either, but I think mesh has got some advantages, and it wasn't that expensive either.
So how much did that cost you? Do you remember?
30 quid. I bought two 10-metre rolls, and was able to cover the 1.9 with that off eBay.
So just in case Francesco doesn't know what you mean by quid, perhaps you explain that to him?
Sorry, £30. £30.
Yes, I saw the net, but I don't know if it is important. I'm looking for a net of an height of 2 meter, almost 2 meter. I don't want make junction of the surface for a question of elegance too. Do you think it's important that the mesh is not continuous, or is different, or several stretches?
I don't think there is, but Wolfgang's probably the man to answer that.
Actually, I'm not quite sure. I was thinking about if it doesn't have to be continuous, and I'm not 100% sure about that. You could actually think about building the total surface from hexagons of maybe aluminium sheets. But it's something I've been wondering whether if completely conductive continuous surface is needed or not. Another thought, if you have a mesh of sufficient size, I could envision, I'm not sure whether that's really working, is that you attach the mesh by essentially heating it up, because this is thermoplastic material, so you can sort of glue it in by just heating it and then pressing it into the printed 3D printed bits and pieces. Something I find this very interesting, by the way. I mean, having a structure done on a 3D printer that will give you a very good accuracy of the basic structure, and you have lots of flexibility how you design your structure. I think it's a great idea, building that from hexagons, forming an overall shape. The coverage. I will take that along for me to think about whether, and ask some experts whether it's really a continuous conductive surface needed. I don't have the answer right now.
I'll make some experiments.
Yes, and as the physics saying goes, the experiment is always right. Talking to theorists.
Yeah, I have a question, Francisco. What type of plastic did you use? What type of plastic did you use on your 3D printer for your construction?
PETG, because I was considered BLA, but BLA is not resisting against the weather and outdoors conditions. PETG is low cost and resist to the weather.
I can confirm that we are using quite a number of 3D printed parts in our overall setup, and for outdoor we use PETG, and we have some parts which have been staying out in the sunlight, in the rain, and in the typical our environment for 4 years, and no problems with that.
I want to say, when it will be finished, I will publish on Thingiverse and the other side of Prosa printables. On printables and on Thingiverse, I will publish the STL files.
That's great, Francesco. Very good. Thank you.
Yeah, it'll be great to see whether the... I would tend to think, Wolfgang, that you don't need a continuous reflecting surface for it to function as a reflector. I think even segmented areas that are not necessarily joined would work effectively pretty much as well, as long as you don't have any gross irregularities between the boundaries and so forth. That would be my guess. And I actually have another question for you, Wolfgang, which I kind of thought a little bit earlier. Do you know of anyone that uses, I know it's kind of outmoded, but the old sort of Krauss antenna? Is anyone actually actively using those? I mean, that it seems like that might be a simple, sort of a larger aperture antenna to construct for like drift scans and so forth. I was just curious if anybody.
Are you thinking about the big ear?
Exactly.
Structure?
Exactly. Yeah, that
Yeah.
type of antenna.
I mean, there's a NORCE radio telescope in France that uses exactly that thing, but that's a big one. I mean, very similar to the big ear. No, I'm not aware that anybody uses that as a smaller instrument in the amateur arena. Actually, that's a good thought to do that. Could work quite nicely.
You would think at least for drift scan and hydrogen type, it might be a little bit more difficult to adjust for the elevation, but in any case to gain some large aperture for drift scans and so forth, it would seem like it'd be even simpler than going with parabolic reflectors. But anyway, just a thought. Yeah,
I mean, I'm not aware of anybody has done that, but that doesn't mean that it wouldn't work. I mean, there's this NORCE, the big one, which uses the scheme, and why not build a smaller one, like 3 meter or 4 meter? Why not?
Did the big ear have a metal floor across that big field?
I don't quite recall. I think yes, but I'm not 100% sure. As far as
it becomes a larger project. Yeah.
Probably you can find out by looking at some old descriptions and so on.
So the question you're asking, Adrian, is whether you can scale up a horn. Is that the question you're asking?
No, it's not a horn antenna. You'd have to kind of maybe look at a picture of the big ear.
Yeah.
It's basically a strip of reflected material, which is sort of in a cylindrical or parabolic shape, okay, placed fixed on say the ground, and then you have the feed horn at what its focal distance would be. So if you would imagine almost like a fence, think of a fence, but kind of covering a circular or parabolic shape. Okay, that would have sort of a focal point, and then you would have a feed horn at sort of that focal point, and of course you'd have to construct this pointing in the general direction that you want to be listening to. So it's kind of a simpler system because you don't have to have an elevated full parabolic shape. So it's kind of like if you were to take the small antenna that Sarah puts out, right? And then just extend the sides out and then just kind of put it on the ground. So it would be kind of a rectangular system, and it would just sort of make kind of a parabolic shape, and then you would just have kind of a feed horn displaced from it. And I don't think that had a metal floor, Ted. I think it was just a reflector at one end of the field, and then it did have feed horns, I believe, on the sort of apex focal points. But I don't think that the field was just an open field, and it just had the reflector at the one end extending along the edge of the other outer end of the field. But I could be wrong again. I have to go back and look at that. Anyway, just a thought. It seems like that might be a simple construction for a somewhat larger aperture and not have to support like a huge parabolic reflector and so forth. Just a thought.
Does it require a lot of space?
Well, yeah. You need the aperture, right? So it depends on how big you want to make it. So it's just that you don't have to extend it essentially vertically. It's just along a horizontal dimension, and so you would just spread that out along whatever area you would want to use for the reflector. Just look up the big ear and then take a look at the picture. That was the very famous radio telescope that detected the so-called, I'm sure all of you have heard of the wow signal, and that was kind of the antenna that was used to receive that. So if you kind of look that up, you'll see a picture of the antenna. So it would just be kind of like putting a fence along whatever length of area you wanted to cover, and then constructing that, and that could be easily done with wire mesh or something, and not have to support it vertically. So it would just got to be fixed. You wouldn't be able to move this. I mean, you might be able to move the feed horn somewhat, and then get kind of a azimuth type of resolution. But anyway.
Yes, I'm looking at the picture at the moment. I'm not sure my wife would accept that in our back garden, But still, it might be very good. One question I did want to ask you is you were suggesting that the reflective surface on perhaps a parabolic surface didn't necessarily need to be electrically connected to the different bits of it. You could just have bits of reflective surface at different locations. Would that not have a problem with the fact that you didn't have a common ground for everything? Or at least, I'm using the wrong terminology because I know the dish is not in ground anyway, is it? But it's at least it's all at the common sort of electrical level across the whole of the dish. Would that not be a problem? This is me not knowing what I'm talking about here. Do you understand?
I think it's not a problem if the hexagon, for example, are connected together, because I think every hexagon concentrated to the focus each what the ear receives. For example, the telescope. I don't remember the new telescope.
The James Webb. Are you thinking about the James Webb? Yeah.
The James Webb telescope has several mirrors that reflects to the focus. They are singular surfaces. It's the same, I think, with RF.
I mean, there are many telescopes where, in the optical regime, where there's a large reflector is made from little bits and pieces, like hexagons. James Webb is one of them. And my first assumption would be it would work the same way for a radio telescope, for a radio reflector. The only thing that makes me a little bit hesitant is I don't recall any professional instrument that has been built this way. There are some, I have to be cautious and really look it up. There are some telescopes where there are individual reflectors which are adjusted by some background back, and it may be that the big telescope in the US forget the name, the big one. This may have that scheme, but I have to look it up. And I always like to look at what are the big professionals doing, and obviously they want to save money and weight and so on, and make it efficient. And there may be reasons why you have to have a continuous surface, but this may be just the reason that they want to use the big telescopes at very high frequencies, so you don't want to have the gaps in between, which would then be doing diffraction at the higher frequencies and at L band. Maybe that's just not immaterial. But anyway, first I found it an interesting thought to build that from 3D printed parts, and second, how to cover the surface, something to investigate. Interesting subject.
I think if the surface is shaped against the hexagon exactly as possible, I think there is not reason that there is not adequate. That's what I think. I must check.
Anyway, Francesco, keep us up to date. That's interesting.
Sure.
You might be interested that while you were talking, I just typed it into ChatGTP. Now I know there's always a question mark over whether ChatGTP gets it right or not, so I have no idea, but I'll just say what it says, just throw into the discussion. Can a radio telescope parabolic mirror be made from a number of hexagons that are not electrically connected? Right, according to ChatGTP, so I don't take credit for it, a radio telescope refractor can be made from separate hexagonal panels that are not electrically bonded together, provided that certain conditions are met, and that this is actually quite common in large radio telescopes. In fact, it's used in the Greenbank telescope and the Atacama large millimeter/submillimeter array. Both use many individual panels to approximate a continuous parabolic surface. The panels are mechanically mounted, but not typically electrically bonded edge to edge. And apparently it claims the reason that this works is because the key factor is not DC electrical continuity, but it's whether the surface behaves like a good reflector at the observing wavelength. And the reality is that the gaps between the hexagons, or whatever you're using, need to be much smaller than the wavelength, so that the electromagnetic wave sees the surface as effectively continuous. And so in practice, at 21 centimetres, you could have a gap of up to a few millimetres between your panels. But if it approaches wavelength over 4, then you start to get significant diffraction effects, and that causes a real problem, according to ChatGTP anyway, at least.
Yeah, I mean, at first glance it makes sense. Always be a bit careful with ChatGPT when it comes to radio astronomy, because I've seen amazing results at times. But I think it makes sense, and I was thinking about the big telescope in the US that has this scheme, and just we need to look it up, and it should be straightforward finding out.
Yeah, brilliant. Well, that was certainly a very interesting conversation.
I think, for example, if you look up the FAST radio telescope, which is the sort of the successor to the Arecibo, the Chinese large ground reflector, I believe that those are individual panels that are actually articulated, so they can actually change the focus and so forth. So that would be an example of where it's not one continuous surface, in my opinion. If I'm not mistaken, I believe that's the construction for it. So you might want to look at that.
The other thing I just point out here that Steve, I'll just read it out because I know his sound's not working, or at least he can't speak into his microphone. When we had our discussion about how much error you could tolerate on the surface, he's commented that root mean square, you can have actually significantly larger than if it's a 10th wave RMS, you can have significantly larger differences in peaks greater than that 1/10th wave, and he suggests that probably the best tolerable error is probably the square root of the wavelength. So that would mean for 21 centimetres, it was 10th, isn't it? It's the square root of the 10th of the wavelength in this case. So we're looking at 1.45 centimetres rather than 2 centimetres. That's his suggestion. Okay. And he's also noted that there's a difference in an antenna's physical area and its effective collecting area, as for example a Yagi antenna has an effective collecting area which is much greater than its physical size. So
yeah, but that collecting area for a Yagi is due more to the fact that you're narrowing a beam. You're essentially, by adding more directors and to the antenna, you're making the beam essentially that you're receiving narrower and narrower. So it's not the area that you're increasing. It's just the focus of the area that you're receiving from.
Yeah, it's essentially a mathematical approach. The same goes for a parabolic dish. I mean, the gain the gain gets larger because it's a narrow beam, and that goes with you can give an equivalent collecting area for a Yagi by taking the same parameters. It's the same story essentially. But
Okay.
anyway, yeah.
Okay,
I think we're making progress on the thought on how building a 3D printed dish.
Fantastic, fantastic. So we already had Steve here. We've got Steve B as well. So our second Steve, is there anything you'd like to talk about? But perhaps his system's also not able to give us audio. Fine, okay. Andrew, would you like to talk about anything? Is he still with us? Or has he gone? Oh, nothing here. Oh, Steve's come back to say nothing to talk about. And I think Andrew got down here, but I think he's already left. Andrew Stowski. Okay, so who have we got now? Ted, is he still with us? Yes, Ted, would you like to talk about anything?
Yeah, I'm still here. So I'm building my horn antenna with an exponential horn of mesh. My hands are roughly intact. It's a horrible job. I'm about a third of the way through. I designed it in sections, and there are 26 sections, sort of gusseted into a cylinder. I made a schoolboy error, which was I soldered the cylinder, I folded the mesh into a cylinder, soldered it onto the can, and then realised I hadn't put the probe in and my arms weren't long enough.
Oh dear, oh dear.
The next schoolboy error I'm going to make is I think it'll be too big to get out of my bedroom. So
that seems as bad as my VLF aerial, where I was going to make it 2 meters, and I was fortunate enough to realise I wouldn't get through the door.
yeah. It's not a sort of project where I want to start taking doorways apart. So
Can you go out through the window?
Another week or two, I'll be able to test it.
No, but could you get it out through the window?
No.
And lower it down on a rope?
It's going to be a thing of beauty.
Oh, well, I'm sure we all look forward to seeing it. You haven't got any pictures so far.
None worth showing. No.
Oh dear.
It looks like it's actually it looks like it's been in the anatomy lab and somebody's been taking it apart.
Well, as a man who spent years actually dissecting dead bodies as part of my medical school training, and actually chatted up my first girlfriend over such a body, perhaps I'm more tolerant than most people.
Oh well, yeah, no.
See Steve's face here.
No, but it didn't make you put them back together, did they?
No, the relationship didn't last very long either, so clearly it wasn't conducive. There's roses, and then there's chatting somebody up while you're dissecting somebody else. Yeah, there we are. So, okay, who else have we got? So I think we're pretty much down the end of it. I think I've got Adrian left here. Is there anybody else that I've missed out? No, because okay, Adrian, anything you'd like to talk about, sir?
Oh, I think I've already spoken enough today. exceeded my allotted time.
Oh, no. It's always good to hear from you. Okay, so I think we've got to the end of everybody, and I hope you all agree. I think it's been a fantastic evening, and I'd just like to say thank you to everybody for their contributions, which have been absolutely marvellous. Wow. So our next meeting is, I've already sent a link out to you, and I think it's the I think I got it right. It's the first Monday in March, which is actually the 6th of April. Sorry, in April. Sorry, the 6th of April. So I hope that you can join me then for that meeting, and look forward to seeing you. Anything you'd like to talk about, please feel free to bring along, or let me know in advance if you'd like a little bit of a bigger session for something specific that you'd like to talk about. Okay.
Exactly.
Just checking.